I will go ahead and get started since I have a few introductory slides. Maybe Michelle, if you want to, send a link to the notes again in a few minutes. But yeah, I'm just gonna go over our goals and agenda for being here today. So let's see here. Okay. All right, I actually didn't practice screen sharing, but can everybody see my screen? Okay, cool. Yeah, so thank you all for joining. Today's session is called Cloudy with a Chance of Science, exploring innovations in cloud-native geospatial technologies. And this is organized by the ESIP Cloud Computing Cluster and the Cloud Native Geospatial Forum, which Michelle is here representing today. So why are we here today? So the cloud computing cluster over the years has been a really great place to share innovations and technology. But I really wanted to find out how we could connect these technologies and see how they could be applied in practice. So today's we'll see some examples of how these technologies have actually improved scientific discovery. So we'll hear from some use cases and technologies that support them. Each topic, which is like a pairing of use case and technology, will have 20 minutes for presentations and then 10 minutes for Q&A. And if you just joined in the notes document, you will see there are links to the Slido polls for each presentation. Cool. And then Michelle, do you want to talk about
Yeah. Yeah, thanks, Amy. Just acclimating us to this space, I'm representing Cloud Native Geospatial Forum, which is under Radiant Earth. And Radiant Earth, it's one of our initiatives to make data easier to access and use. And so the next slide just is an intro to Cloud Native Geo, where it's like very simple. We're just trying to create the future together. And one of our big things that we have coming up is our in-person conference. So this will be this spring, starting the 30th of April to May 2nd, in Snowbird, Utah. So tickets are live. There's early bird pricing till the end of February. Go check out that link to learn more. But yeah, we love these efforts. We're actually taking this session and kind of expanding it at like the concept of this work at the conference. It's going to be one of our main tracks, kind of that bridge. We've got bridge between science and technology, and then the cloud native geospatial in practice. So would love to see some of your lovely faces there. And with that, I'll pass it back to Amy.
Thanks so much. Yeah, so asking questions, I realize you're not going to remember all these codes. So the quickest way to access the Slido links again is in that notes document on the second page. Yeah, and then with that, the first topic is going to be about SOFAR Ocean and virtualization at CDF. So I'm going to stop sharing and pass it off to Camille and Mariah.
Okay, thank you. Let's see. Sharing going. All right. Great, thanks everyone. I'm excited to be here. My name is Camille Teixeira. I am a software engineer at SOFAR Ocean, and I have with me.
Hi, I'm Mariah. I'm also a software engineer at SOFAR Ocean.
So we are going to talk a little bit about the massive amounts of NetCDF that we ingest, produce, and store to provide marine forecasts to both our internal services and also to the world at large. So SOFAR Ocean is a marine data company. Our goal is to use data to power a more sustainable future. The oceans have historically been a blank area on the map, and so one of our goals is to understand it better. And we do that by designing and producing ocean sensing hardware, such as wave buoys and current meters. We sell these devices to research groups, to aquaculture, ports, and government agencies, but we also manage our own fleet, our own private fleet of them across the world's oceans. With the data from this huge sensor array, we develop and run very accurate marine weather forecasts. Primarily today, they are wave forecasts. And then we serve these forecasts to Wayfinder, which is our voyage optimization platform. It provides guidance to large vessels like bulk carriers. Our goal is to reduce fuel use and emissions in maritime shipping. So we've got like a lot of moving parts here, but the one that we are focused on is weather and forecasting and the data that is input and output by that process.
We're specifically both software engineers on the weather team at SOFAR. The weather team at SOFAR is comprised of a mixture of scientists and software engineers. Together, we manage and develop our forecasting system, including the ingestion, processing, analysis, storage, and service of the outputs and inputs to this system. Our goal on the weather team is to develop world-leading marine forecasts for short to medium-range time horizons across the global ocean and provide timely access to our data for our operational and routing teams and services. Because we're always striving to improve our forecast, whether it be increasing the resolution spatially or increasing the forecast horizon, compute and storage costs are continuously increasing. This means we produce and store hundreds of gigabytes of new data on S3 every day. Even with aggressive exploration and glaciarization policies, S3 storage is one of our largest single costs to our forecasting system. Due to our use of open source weather data, our proprietary data network, and our advanced weather models, we are able to provide a forecast with up to 50% improved accuracy compared to other models. So we ingest data from a variety of providers, input it to our forecasting system, and produce files which are all stored as NetCDF. Each of these files has the spatial extent of the entire globe, and when then we post-process this data so that it can work for all of our use cases, which I'll talk about a little bit. We partition the forecast into separate files for each hour and for each component individually, such as significant wave height and mean period and what other ocean variables that we're producing. We partition like this in order to support access to small temporal portions of a forecast, because it would be very inefficient to collect an entire 240-hour forecast file when you're only interested in the first 6 hours. This means that at this point, we do not have the ability to subset the file spatially, and so we do some additional processing. In order to allow for faster lookups in space, this global NetCDF data that's produced is cut into smaller spatial chunks and stored as flat arrays of JSON, which allows for constant time lookups of coordinates in the array. Coordinates such as latitude, longitude, and time. And we provide data in these two formats because NetCDF data we need to feed back into our model run for the next forecast and to use it with our internal skill assessment tools, and also to maintain an industry standard that the science people are used to dealing with. We also serve this data as spatially indexed JSON blobs in order to provide visualizations in a browser for our routing tools and for our public dashboards, and then also to support our public API for point requests in lat, long, and time. We load these JSON blobs into memory and extract a point to return, and we do this for millions of requests a day.
So we're here to discuss to posit some of the problems with this, or the challenges with this system. We store a lot more NetCDF data than we store these JSON blobs, even though the JSON blobs are a little easier for us to work with. We would like to be able to access all of our data in the same way. We have good discoverability for our JSON blobs, but not for our NetCDF files. We also have split access patterns. We have a science and NetCDF pattern, and we have an everyone else with JSON pattern. This means we're constantly reinventing the wheel, as the science and NetCDF pattern is mostly a stack of Jupyter notebooks and one-off scripts developed by science or analysis team members. And so our post-processing pipeline is awkward for experimental data. So it doesn't often, experiment data doesn't often become these JSON blobs. And the main issue that we are facing in the future is that our data is getting bigger. The spatial resolution of our forecast models is increasing. Our first model put out a couple of years ago was a 0.5 degree resolution. We're now operationally producing forecasts at 1/4 degree, and we'll be rolling out 1/8 degree and smaller later this year. So we've already cut the size of our JSON blobs down by quartering the spatial index, but the netcdf files continue to increase in size. They're not getting any easier to move around or cheaper to move around, and they're challenging to move around for analyses or to access for analyses. Downloading a 3 GB file on our shared office Wi-Fi takes more time than most people are willing to give. So what we would like for the future and what we're hoping to learn more about is how everything in netcdf could be uniformly accessible. We'd like to be able to pull data into an analysis, a modeling run, or a browser application without storing multiple file formats. AWS S3 storage is one of our largest costs. It is, we think that ZAR-like structures and access would be beneficial, but we still need to maintain netcdf as an input to the forecasting system. So storing both netcdf and ZAR, for example, wouldn't be tenable from a storage and cost perspective. We also would like performance small chunk access. Point in space and time requests are a huge part of what we serve in our external and internal APIs. And I know that this is accessing small ranges of gridded data is a challenge for many, many different data formats and vehicles. So, thank you. We will turn it over to, I think, Sean next.
Yeah, Sean, if you're ready, go ahead.
Yeah, for sure. Can everyone see my slides? Yeah. Perfect. Thanks. Thank you very much, Camille and Mariah. That was excellent. This is like a softball setup, I think, for some of the virtualization discussion that we'll have here. I think most of this presentation was originally intended to discuss legacy files associated with large producers and distributors like NASA and NOAA. But I think the application of virtualization is equally usable for organizations like yourself. So hopefully this will be of some good reference. I'm going to talk today a bit about virtual ZAR, which is a way to create virtual ZAR stores using X-ray syntax. So just like was discussed in the previous presentation, we have a huge problem in our ecosystem of legacy file formats. So we have so many legacy file formats, but we don't want to work with them in the traditional ways. We want to treat them as efficient, cloud accessible, single cohesive data sets rather than individual files. And just like was presented before, ZAR is a better storage approach for the cloud because it provides a clear separation between data and metadata. It supports scalable parallel I/O, and it natively supports a lot of the cloud optimized access patterns that we like to use for forward-looking applications. But for reasons of cost or operational constraints, most users don't want to change or can't change the existing distribution formats that they're using. So this is the experience we have today, which was just outlined. We have often netcdf, HDF, or GRIB files distributed on a per time step basis, and we have to understand what the file naming pattern and the distribution format of these files is if we want to work with them as a single data set. So this is the experience that people want to have. They don't want to have to know the internal individual files and how to find and access those individual files. They want to just perform simple analysis operations across the full breadth of their data set. So how can we get to this? We can use ZAR virtualization. We want to create a ZAR-like layer over the top of this over the top of these legacy files, and use ZAR metadata and pointers to the byte ranges inside these legacy files. So I'm guessing that given the audience here, a lot of folks are already familiar with Kerchunk. Our colleague Martin Durant at Anaconda was the one that really pioneered this concept and this approach. The Kerchunk approach uses a different way to make a ZAR-like layer. So it has some internal abstractions where we can find the byte ranges inside an internal or inside a legacy file using single HDF5 to ZAR or some of the other legacy file format readers. Internally, they're represented as a nested dictionary, and we can combine those nested dictionaries into a single large data set using multi-ZAR to ZAR. And then when we're finished with this combination step, we can write all of that information out as a chunk reference file. And the result of this operation is a sidecar file, which behaves like a ZAR store when you're reading it through FSpec. But we've been working with Kerchunk for several years now, and we've tried to implement Kerchunking of lots of large data sets that are composed of legacy files. And we've run into a few issues or pain points that Kerchunk's design has caused. So some of those are the fact that concatenation becomes quite complicated in some cases. Some of the store level abstractions that it uses make some concatenation operations hard to express. The API itself, especially the multi-ZAR to ZAR function, is a bit bespoke and difficult to reason about and a little bit overloaded in what it does. The in-memory dictionary representation is not necessarily the best or most memory efficient format that we can use to represent these files. And the output files that we produce when we create a Kerchunk reference file are not real ZAR stores. They can only currently be understood using FSpec, and which is only accessible through when you're using a Python-based language. So we wanted to take this concept of this concept of Kerchunk, and really modernize it and make the API a little bit easier to use. So we know that Xarray already has excellent array concatenation logic. So we wanted to make this this virtual reference concatenation experience as easy as using Xarray concat. And at the same time, we wanted to produce a more efficient in-memory representation of these byte range pointers that can scale to the sizes that we need to represent some of these large legacy data sets. And finally, we wanted to output true ZAR stores that follow this ZAR specification so that any language that can implement the ZAR specification can be used to read from these stores. So at its base level, a ZAR store is really just metadata and compressed chunks of bytes. But Martin in his work on Kerchunk has really demonstrated that these bytes don't necessarily have to live inside of the ZAR store. They can be bytes that are outside of the ZAR store, and we can use pointers to show where these bytes are located. So the simplest representation is a ZAR store with a list of paths and offsets for the chunks within those files. And we call that a chunk manifest. And you can see an example of what the JSON for a chunk manifest would look like here. So what was virtual ZAR intended to do? We really wanted to simplify this reference concatenation problem. And we recognized early on that it's just an array concatenation problem. So when we combine references, we really just want to be concatenating arrays using Xarray's logic. So internally, virtual ZAR has an array type that Xarray can wrap called a manifest array. And internally, that manifest array wraps a chunk manifest, which is really just an object containing pointers to the data in our legacy files using a really highly efficient internal memory representation. So up until recently, virtual ZAR has really only been an abstraction. So it allowed us to create and generate references for legacy files and then combine them in memory using Xarray concatenation logic. But when we wanted to write the results of that concatenation out into a single unified structure, the only way that we could serialize that was to write it back out to Kerchunk, because the current ZAR specification doesn't have any way for us to represent these data sets or serialize these data sets. But I think Ryan is going to talk next about IceChunk, which is a ZAR-compatible store that they've been working on with Earthmover, which allows us to create version-controlled ZAR stores. So it's essentially an Apache Iceberg, but for arrays. I think Ryan can explain this better. But they built in support for this virtual reference concept. So we're able to serialize the virtual references that we generate in virtual ZAR into a store. And we're able to commit virtual refs into IceChunk and tracking the changes. So we have a readable version of this directly. And so I'll turn it over here to Ryan to talk more about what they're doing in Earth.
Okay, great setup. This is so fun to have the problem statement motivated by a real world use case, and then have some solutions that just can slide right in. Okay, so I was told that we have just a short time, so I'm going to try and condense this and skip all of the intro and all this stuff. We know that archival array file formats struggle in the cloud. Typical forms we use for raster data or gridded data are things like HDF, NetCDF, or GRIB. In the weather space, these are prevalent. On the other hand, in the cloud, we want to use object storage. You know, so far engineers mentioned that they're spending a lot on S3, but they would be spending 10 times more if they wanted to use mounted disk volumes in the cloud. So S3 remains the most cost-effective way to store big data in the cloud. But those archival file formats don't work well in cloud object storage due to high latency of the HTTP calls associated. So Sean mentioned ZAR as a good choice as a cloud-native multidimensional array format. ZAR is a scalable cloud-optimized format that really allows you to spread arrays over many objects and scale out your arrays to arbitrarily large size, read and write those arrays in parallel, and plays great with cloud object storage. And we see this used heavily to store weather and climate data today in the cloud. However, there's some problems with the status quo, and Sean did a nice review of what some of these are. You know, exabytes of data are still being produced in these archival formats, and if the data providers change the way they provide data, that's going to be a 10-year evolution, right? GRIB and NetCDF are WMO standards. They're not going away anytime soon. We like ZAR. It's promising, but it has some limitations. The first one just being the need to transform all this data, which is a cost a lot of folks just accept and choose to bear and then reap the benefits of ZAR. However, there's still some other issues that are preventing ZAR from really fulfilling its potential that have to do with how we update those ZAR data sets that make them a little bit unsafe to use in an operational context. And I'll say more about that. And so with these large ZAR archives, it can become hard to detect and fix corrupted data as well. And so, you know, what we see is that our community is still not really taking advantage of these cloud native data systems. If we were, it would have been a no-brainer for the SOFAR folks to just be using cloud native technology rather than the NetCDF based technology, which is, you know, 30 years old at this point. So within this landscape, we're really excited to be launching IceChunk. It is an open source cloud native transactional tensor storage engine. What a mouthful. I'll try to explain what that means. But I'm going to have to cut some corners due to time. So here are the resources you can use to find out more about IceChunk. We have a very verbose website at icechunk.io, and there's a GitHub repo. If you find yourself on the GitHub repo, please don't forget to give IceChunk a star. IceChunk works together with ZAR, acting as a storage engine under the hood. And it's compatible with both Xarray and virtualized ZAR. So as an end user, you don't even really have to make many changes to your workflows for reading or writing data to use this. IceChunk is fundamentally a Rust library with just a Python wrapper on top of it. And that means that it also works with Rust, of course, and also we have some Julia interoperability in development. And it's 100% open source, licensed under Apache 2.0. So real quickly, what is a transactional cloud native storage engine for ZAR? So if you've used ZAR, you may realize it basically just uses a key value store to store both metadata and chunk data. And today, if you use ZAR with object storage, you're likely going through the fspec library, which is responsible for translating those ZAR keys into, data in S3. And the way Ice Chunk works is it just slides in there. Instead of using FS-Spec and those stores, use the Ice Chunk store. And in addition to managing all the I/O from cloud storage, it also reformats how the data are stored under the hood and uses a more clever schema for the underlying storage format. And so what does this enable? ACID transactions for ZAR data. So this allows us to safely read and write large data sets concurrently without any locks or coordination and roll back any problematic updates that we might have made. This is a huge peace of mind for data engineers. Using the same basic features, we can do data version control with this ZAR data. We can publish tags and we can do branching of our data. All the things we do with Git, we can do with Ice Chunk. However, for the sake of time, I'm not really going to be able to dive into these, and I'm going to focus on what we're here to talk about, which is virtualization. So as Sean mentioned, Ice Chunk can work together with Virtualizar as a sort of optimized on-disk serialization format for these virtual references. And then finally, Ice Chunk gives some really big performance benefits when working with cloud object storage, independently of whether they're virtual or not. So, what does this virtualization really mean? I see this as the ability to remix existing files into data cubes in a flexible way. So fundamentally, as Sean said, we can build these virtual data sets pointing at underlying GRIB, NetCDF, or HDF files without actually copying all the data. And when we read those back using Ice Chunk, it's really indistinguishable from whether we had written sort of native virtual data sets. We can also, native ZAR data sets. We can also incrementally update and overwrite these virtual data sets, either with more virtual chunks, with more native chunks, make metadata changes in a rather flexible way. And as I mentioned, this integrates with Chunk and Virtualizar. So, don't have time to give a real code demo, but just to show that this is real, here's a project we've been working on with Amy and the folks at DevSeed and NASA through the Impact program, where we're building some virtual data sets for the GPM iMerge data. And so here we're combining, a large number of underlying NetCDF files into one virtual Ice Chunk backed store. We can open that up with X-Ray. We can query the data really fast. And so, this is an exciting technology for data providers and anyone that is really storing large volumes of NetCDF data in the cloud. Last real slide here. Ice Chunk is pretty fast. It's, of course, I'm not going to go through every detail here, but here we're comparing essentially the time it takes to read data. Here we're directly accessing HDF files without any virtualization involved, any chunk, any of that. So that's sort of our baseline. And we're plotting the throughput in megabits per second or gigabits per second. And so here we're down around 100 megabits per second. And just to cut to the chase, with Ice Chunk and the latest ZAR release, we can get throughput reading from cloud object storage of 7 gigabits per second, which is getting pretty close to the network capacity of the EC2 instance we're running this on. So really reaching that sort of hardware saturation point. So I think I should probably just stop there. I can say a lot more, but for the sake of time, let's move into the Q&A. And I hope I've at least convinced you to look into Ice Chunk and learn more about it, and be happy to answer any questions.
Thank you so much, Ryan. Yeah, and Ryan has some great longer format presentations on Ice Chunk on both the Pangeo showcase and the Ice Chunk, the Earth Mover webinar series. So if you want to learn more, I encourage you to also go and watch those. I don't know, Ryan, if you want to find links for those and put them in the chat, I can do that later as well. In terms of questions, we just have 2 questions. So the first one is, I think, from Cassandra about looking for storage options for large file sizes and reliable cloud storage recommendations. So I was hoping to actually just quickly follow that up with a follow-up question, which is there a reason, are you looking for something different than cloud object storage? Is there a reason why that is not a good fit? Looking for where to store your data. Are you familiar with cloud object storage? I would look into like Amazon S3, like simple storage. And yeah, happy to share some information about that. And yeah, I'll reach out and send you some more information about how to get started with that. And then from Ian, this is a great question. Are there still disadvantages to using HDF5, NetCDF4, and S3 when you have good sidecar files like you can create with these chunk manifests? I think either Sean or Ryan could well answer that question.
Yeah, I mean,
I'll jump in. Oh, go ahead, Sean.
I was just going to say, I think Amy can also answer this as she's recently been doing surveys of like the full volumes of NASA data to try and discover what some of the drawbacks of the existing HDF files are. But yeah, Ryan, if you want to jump in.
Well, the SOFAR engineers highlighted a goal, which is that they want everything to be fast for any type of query, whether it's a spatial query or a time series extraction query. And that's a big ask because when we're talking about hundreds of terabytes of data, all of those bytes just can't be close together. There's no way to do it so that every byte of data is close together. So, what we like to do when we're building native ZAR data sets is to rechunk the data to support more flexible query patterns. Whereas when we are constrained to use the archival files and the virtualization approach, those internal chunks within those files can never span more than one file. And we're usually getting one per hour or one per day or something like that. So there's fundamental constraints on what chunking we can use with the virtualization approach. And to be totally honest with what you're doing, since you're committed to ingesting this data, I would be building native ZAR data cubes as you ingest the data, throw away the original NetCDF files, and then generate them on the fly when you need to run your modeling, rather than persisting the NetCDF files themselves as your original, as your primary archive of data. It would be a little different if you were able to use existing NetCDF data that was already hosted in the cloud, say by NOAA as part of the NOD program or something like that, because then someone else is footing the bill. But as long as you're paying, for half a petabyte of S3 storage, and you're building a data pipeline to do that ingestion, I would be optimizing the hell out of, all of that storage. So it's totally dialed for the queries that you want to make, rather than feeling constrained to have to store the NetCDF files. That would be my honest recommendation in your situation.
Okay, great. There is one other question from Slido. I'm going to paste it in the chat, and if anybody has a chance to answer it, that would be excellent. But I'm going to move on to, thank you so much, Camille, Mariah, Sean, and Ryan. Let's move on to the second topic, which will be led off by Dennis Willett.
Awesome. Thank you guys so much all for coming today. Let's test screen share here. Is this coming through? I see some nodding heads. Awesome. Cool. Thank you so much for coming today. I think you'll find some similar themes echoed in this presentation. We're going to talk about finding droplets in the cloud, basically trying to separate out raindrops from massive cloudy science on the cloud. Another way of thinking about this is very similar to some of the problems and discussions we just had. How do you find just the data that you want in a sea or a cloud of data? How do you find megabytes and petabytes? So that's the context we're going to be starting with here today. And we're going to be coming at it from an interesting perspective. So I work for the North Carolina Institute for Climate Studies, and we work extensively with open data in a couple of different avenues. So we support the technical support unit for the national climate assessments. We, through our role as a cooperative institute, we support NOAA research at NCEI, and we're also the data broker for the NOAA Open Data Dissemination Program, which is kind of what we're going to be focusing on today. So at our institute, we support NOAA's mission to provide environmental data at scale to anybody who wants it in a free and open manner through the NOAA Open Data Dissemination Program. And the way that we do that is we work very closely with NOAA to take their data and help move it and provide the infrastructure to be able to transfer it to the three primary cloud providers that we are working with, Amazon, Azure, and Google. In doing so, we have been doing this for a little bit now and have accumulated over 67 petabytes of data holdings that we manage for NOAA across these different public cloud providers. We support petabytes of data access and billions of requests on a daily basis to these data. As we have expanded over the past few years, the holdings have also expanded. So today there are over 300 NOAA datasets that we manage across these three major public cloud providers, and they really span the entire Earth system. We have atmospheric data, oceanic data, period of record climate holdings, forecasting products, model data, surface observations. It really runs the gamut. And this is incredibly diverse and incredibly useful for doing Earth system science. But we want to be able to support access to these data. And currently, we have these data across multiple clouds and multiple accounts and in multiple regions. And it's very difficult sometimes to be able to find the data that you'd like. And at the ESIP Stack Summit in 2024, we were asked to imagine a world where finding this data is actually easy, it's fast, and it's seamless. And we started talking about this SuperStack catalog, which is sort of globally searchable, where we have the open data in this one environment that supports open data. Oh, excuse me. Computer's thinking for itself here. It's across all cloud providers, and it has API access so people can actually find the data that they need, find the droplets in the cloud. So we've been working with the AWS Open Data Program. Thank you very much for the support with this. Radiant Earth as well, thank you, and DevSeed as well, to kind of be able to put the pieces together and start building prototypes to be able to basically add a searchable interface using Stack to access these data in the cloud. And what we're going to be talking about today is some of the challenges that we encountered thinking about scaling this. So if we look across data holdings, we have a number of different data sets. Here are some of the most popular and some of the largest ones. And what we have here is numbers of objects. So for the GOES geostationary satellite data, we get approximately 600,000 new data objects a day. And currently have over 800 million of them. You can look at some of the daily changes in holdings for some of these other data sets, but currently we receive approximately 25 million new objects a day on Nod, and we manage over 10 billion objects across all three cloud service providers currently. So when we think about how we actually put this infrastructure in place, we want it to scale to this level. And so we've been working over the past couple months to think about how we build Stack, scale Stack, and then actually serve the ability to search for these data at scale. And in thinking about building a spatiotemporal asset catalog at scale, there's kind of three key parts to this process. There's actually scanning the data, identifying the granules, taking the metadata out so we can then identify how to get back to those data objects, doing this in a scalable, fast pipeline, and then providing access to it. And we've been very fortunate that the community has these amazing tools available, things like Stack Tools packages, the Stack Tools pipeline, and then also the EO API. As we've begun playing with these, we've realized that while these are all really great tools, when we begin to implement them at scale, there are a number of additional considerations that we have to think about in terms of how we continue to scale them to meet the needs, not only of the people using the data, but also of the data providers themselves. So if we think about the number of objects we're processing on a daily basis, like we just discussed, and we think about actually scanning each of these granules and putting them together into a pipeline, we also have to consider the data formats that we're working with. You just heard a great presentation on virtual ESR and the benefits of that. And that really is potentially of interest to us because, as I mentioned, there are 300 of these NOAA data sets on these different cloud service providers that span all of these different types of data. As a result, we manage a plethora of different data formats as well. You've heard a lot of the standard ones in NetCDF, HDF5, et cetera. We also manage a number of unique formats and other common formats as well. And ideally, we would like to provide seamless interfaces to a wide range of these. These different data formats correspond to a wide range of different data types and sources. So data that come in at different scales, different locations, and we'd like to be able to unify them in sort of a consistent scheme so that you can connect data across these different sources. Ideally, you'd be able to connect video and genomic data from the fisheries service with information about the oceans from Argo buoys, for example, and being able to do that in sort of a consistent manner. When we think about this, we realize that the production systems and the pipelines that generate these data and provide them to the public on Nod, it's a substantial capital investment, and changing that is really not feasible. So the question that we have is really, can we keep these formats do it in such a way that we can kind of unify and standardize the way that we access them in a searchable way through a unified stack interface or through some of the different options that you just heard about, and we'll follow up on here as well. So that's one of the big sort of questions that we're setting up here for a discussion, and we can talk more about this. The other aspect of this is once we have this in a consistent format and are able to identify where these data objects are, we need to be able to serve that information to the public. And so we've played extensively with the EO API using PG Stack, et cetera. Thank you very much, DevSeed, for all the amazing work you've done on this. This works great. It is performant. But when we begin to scale it at the scale of Nod for 67 plus petabytes over 3 cloud service providers with over 10 billion objects, the costs involved in actually running this at scale become prohibitive for the organization and being able to do that. And so we are wondering, can we leverage our existing infrastructure, which is based on cloud object storage, S3, GCS, containers on Azure? Can we leverage that existing infrastructure and the sort of existing financial infrastructure that supports this through Nod to be able to serve information about how to access data objects through an S3 storage layer, for example? And so we've been playing here with, excuse me again. We've been playing with a variety of different options to be able to do that. So we are very interested and working on developing prototypes for running Stack at scale. Looking forward to chat more about that. The 2 big things that we're working with currently are those 2 questions. Can we use our existing formats, and how do we do this at scale using existing object storage infrastructure? Really appreciate this session, the conversation that's coming out of it. I'm looking forward to chatting more about this, and I will turn it over to the other participants for conversation. Thank you.
Awesome. Thank you, Dennis. Sean, go ahead.
Sorry, I thought we were going to get Kyle first there.
Whichever you guys prefer. Do you think it makes sense for Kyle to go first? Then Kyle can go first.
Yeah, let's go Kyle first because some of my stuff is duplicative with the initial virtualization presentation.
Sure. Kyle, does that work for you? Nice. Thank you.
Yeah, can you hear me? And can you see my slides?
Yep, can hear you and see.
Awesome. So hi, I'm Kyle. I am a cloud engineer at Development Seed. I do a lot of work on GeoParquet and Stack and some of these related technologies. And so I'll just talk for 5 minutes on a little bit of background on GeoParquet and how we think it's has a lot of potential to be used for Stack. And so as some background, GeoParquet is a file format for vector data. You could think of it as similar to shapefiles, to flat geobuf, to geopackage, any of these formats that stores points, lines, polygons, and so on. It specifically is designed for really large vector data because it scales very well, it has very good compression, and is cloud native. And so I'll cover a couple different topics that GeoParquet is cloud native. It's very easy to read and write directly from the cloud. It's fast to read and write even when you're not using it on the cloud. And we can integrate it with Stack. And so the way that GeoParquet is cloud native is that it has these internal chunks. And so the same way that Czar has internal chunks that you can kind of access one specific section of the Czar array without having to load the entire Czar array across the network, GeoParquet also lets you do. And so you can select either vertical segments in the sense of you can take 1 column or 3 columns of your table and not need to load every column if it has, say, 100 columns. And you can also choose specific chunks of the rows. And so if you need maybe the first 10,000 rows and out of a 10 billion row data set, you can do that very efficiently. There's also more work recently to enable spatial partitioning in GeoParquet. And so if you want to store a very large data set that's geospatial, that has some spatial component like Stack, we have scenes that may be across the world, then you want to very quickly access scenes that have based on say a bounding box query. And so we can use this in GeoParquet data sets. Here, this is an example. If you're curious, you can go to explore.overturedmaps.org and click on Download Visible. Now, this is using cloud or a spatially partitioned GeoParquet in the cloud and downloading just this portion of this big data set. This is Overture Maps is an extension of OpenStreetMap, and that's loading the data directly out over the internet. And so you can imagine that you are taking this 2.4 billion row data set, at least for the buildings data, and accessing all of that data directly. And so we can do the same stuff with Stack. GeoParquet is also very fast to read and write. Here's a simple comparison of this with other common spatial file formats. So it's both say it's about the same time in Python to read this into GeoPandas as flat GeoBuff, but it's way smaller than the relevant flat GeoBuff file. We've also been doing some work to integrate this into Stack. And so here, this is at Stack Utils, Stack GeoParquet, there is a repository and documentation website, both for the specification of how we actually lay out Stack in GeoParquet and how we it also contains an implementation in Python of doing this conversion from Stack JSON into Stack GeoParquet. This is kind of a tricky process because Stack is JSON and every Stack item could be a different schema, meaning it could have different properties, it could have different assets. Whereas in Parquet, Parquet works best if you have all of your rows having the same columns. And so you really want to have one GeoParquet data set per Stack collection so that the rows all have the same columns. And then each of the underlying Stack nested properties are taken into their own Parquet column, which means that if you want to have to access the red, green, and blue asset URLs of some data set, that's extremely fast to read in because you can ignore all the other data in whatever data set you're using. We're also doing more work internally as exploration and development seed to both use Stack as a query backend, that we'd like to essentially have a Stack API that instead of having a database hosted that you need to maintain to use these GeoParquet files directly. And in the future, it'll be more of an advanced topic, but to use Stack in Apache Iceberg, which is a layer on top of Parquet, to enable adding, removing, and deleting rows. This is very similar to the IceChunk way of supporting these transactions on top of ZAR, so that similarly to ZAR, GeoParquet itself is more of a read-only format. You can't edit the ZAR data directly, and we use Apache Iceberg to manage the mutating data, which will hopefully work very well with Stack. And that's all I have. Happy to answer questions after Sean goes.
So I'm furiously updating my presentation behind the scenes based on what everybody is talking about. So I actually quickly altered the title of this because I think this is Dennis provided a great overview of what's happening at the nod. And I'm going to talk a little bit about some of the comparisons and contrast between using Stack versus virtualization when we're dealing with indexing and archiving these large data sets. So yeah, as Dennis outlined, like the data that NOAA creates and that the nod distributes is really invaluable to scientists, businesses, and decision makers that need to understand our planet in real time. It's a huge the data sets that they're producing provide a huge level of value to everybody that's able to access them in the public data buckets. And yeah, this non-publication of this data is a huge step forward for data consumers from a technical perspective. But the archival data formats and the lack of standardized central metadata, as Dennis showed, really leave this treasure kind of locked away from users that don't have specialized expertise in these data sets and in these legacy file formats. Users really need a map to understand where this data is and what data is available. I like the raindrop analogy that Dennis used. I think that's a good way to phrase things. We have a few options to build this map. So the first is the stack specification, which we talked about. It's a common language to describe geospatial information so that it can be more easily worked with, indexed, and discovered. And I'm a little bit torn talking about this in this presentation because the bulk of my work in the past has been building the tooling associated with the stack specification and the specification itself. So to propose alternatives and to talk about some of the limitations with stack is a little difficult for me. But I do think that within some of the data sets that the NOD is dealing with and publishing, there is some other options that may work better than stack for some of their use cases. Stack was originally designed with a focus on satellite observations with small discrete footprints. But a lot of the NOD data is really not in this model. It's more n-dimensional data with multiple variables that are constant over space and time and are distributed as gridded data sets with a regular grid. So we've seen this with some of the presentations today. Due to the operational nature of NOAA data production, all of these data sets get produced as single archival files per time step for a global grid. But like we outlined before, most users don't want to work with single time steps. They need to do analysis or understand the planet over space and time and look for patterns that are spatiotemporal. So data distributed as files requires users to learn how to find the files relevant to their analysis. In the case of NOD data, this means millions of files with varying formats and naming conventions. So Stack can provide a map for this data and allow you to find the files that you're working with. But in the case of gridded data sets, users want one step beyond that. They don't want files, but they want a virtual ZAR archive, like we talked about before. They want a single cohesive data set that represents all the underlying files as a single data cube that they can work with in a consistent way. Another problem or kind of difference between Stack and the virtualization technology in this case is the verbosity of the representation that we're using for the metadata associated with these files. On the Stack side, the JSON structure that we use to represent the contents and the metadata associated with these files is pretty verbose, and it's really modeled around older Earth observation data sets. We've extended it so that it can work with n-dimensional data sets, but we're still using what I would call a very memory inefficient representation. And as Dennis has outlined, this can become problematic when we're working with the scale of data sets that they are. Kyle's work is really improving the underlying storage and access performance for some of this verbose representation. But we probably don't need all that verbosity when we're representing some of these data sets. And beyond just being able to have a better internal representation or a simpler access point for these data sets, I think the real future of this, or the real benefit that we're going to see from virtualization in contrast to Stack, is just the simplification of engineering for people that are building applications on top of these data sets. Currently, Stack and the Stack tool sets that we have really do allow us to understand and access large volumes of data in a pretty consistent way. But it's really just allowing us to know what data is there and where it is. It's only metadata. And we're still restricted to using legacy drivers to access the underlying data itself. So if we get metadata records about a collection of HDF files, we still need to use HDF drivers in order to understand and work with that data, which requires engineers building applications on top of that to understand how those drivers function. In the case of virtualization, we're kind of just bypassing that entire step and allowing engineering teams and people that are building applications to work with a single consistent API, which is ZAR. So again, I don't think that virtualization is something that we do instead of Stack, but I do think that we're going to see a complementary approach for large organizations that we know going forward.
Awesome, thank you. So there's been a lot of activity in the chat, so definitely recommend reviewing some of that. Very interesting stuff about what NASA's CMR is exploring as well. I don't see any other questions in the Slido, but I did have one myself, so I'll kick it off with that, which is I think directed at Dennis, which is what are some common challenges that you all have come across when creating stack metadata for the varied collections that in NOAA's catalog?
Cool. So that's a great question, and I'll build off that and tie it back into the additional presentation here really quickly. So the first step of building these stack catalogs is really the granular generation, and actually that's been one of the most interesting part of the challenges, because it's not just a technical challenge. There's a lot of great technical tooling for a lot of data sets, but actually less than 5% of the data sets that we manage through NOD currently have these sort of stack granular packages sort of pre-built by the community. And that's great, but a lot of these data sets are very domain specific, and by domain I mean scientific area specific, where there are domain experts that have a lot of built up knowledge over decades of experience on what metadata is important for finding what data and how to get it out of the file formats. And so what we've discovered is a key aspect of that is actually connecting with the subject matter experts of these different data sets to learn more about that and work with them to make these sort of the granular scanners to be able to pull out this metadata. There are some ways to sort of get around and automate that, but really to get quality information, that's kind of the best way to approach it. The other thing that I think is worth mentioning in a slightly different way, because it's a really key point. Sean and Kyle, you both touched on this, but the part of the scaling issues that we're dealing with in NOD deal with just the sheer number of objects that we have. And when you start to put together a massive catalog to be able to search across all these objects, it really helps if you can collapse objects so you don't have as many objects to deal with. And one of the really nice things about the virtualization combination with the GeoParquet performance is that if we're able to take a large data set like a multi-petabyte geostationary satellite data set and collapse it through virtualization into one access point that people can access through Xarray using virtually ZAR, that similarly collapses the number of objects that we have to deal with and search through something like a stack catalog interface. So these two technologies are really complementary in the sense that using them together not only creates a better user experience in terms of how you access the data, but it also solves a lot of the sort of scaling problems on the back end in terms of how manageable the data sets become, not just from the side of making it accessible to people, but also the user experience and how fast they can access the data. So I just wanted to highlight that as well.
If anybody else, we do have a few more minutes for questions. If anybody else has a question, feel free to also raise your hand. But just a quick follow-up to that, I suppose, would be, so now we have all these pipelines for your experiences creating metadata for all these varied formats. Do you feel like sort of there was an original design flaw with these formats in terms of like there's too much flexibility and all of the standards have not really been like enforced fully? And like, yeah, that's sort of my general question. Like, how do we sort of move toward the place where there's more standards and like less chance for people to get confused and learn about new format, learn about a new collection?
I guess, do I get to touch that one first? I'm looking at the meat pen here. So one of the things that this cloud native geospatial community has enabled, which hasn't really existed even in the past decade or so to the extent that's happening now, is that we're able to connect different scientific domains together. And so far in the presentation kind of mentioned the oceanography. Like for centuries, the ocean was just undersampled. Well, we're beginning to address that problem, but in addition, we're also now able to connect ocean data with land surface observations, with remote sensing data, with like we can combine these data sets and connect it. And really it's only because of the technologies that we currently have accessible, it's really only been in the past 5 to 10 years that we're able to do this at scale. And historically, all of these different sort of scientific subdomains came up with the best format for them, which makes perfect sense. Like NetCDF is a great format for what it was designed to do. These formats are great for what they were designed to do. We're asking them now to do things that were outside of their original design specifications to be able to facilitate all of these different data connections. And I think the community coming together from these different domains is really interesting so that we can begin thinking about ways of standardizing the connections between these data sets. That doesn't necessarily obviate or mean that these other data sets are bad or that they're obsolete. They still have an incredible purpose. It's just we need to figure out ways of working with them so we can connect data sets across these different domains and do some really cool research and actually make some change in the process.
Yeah, awesome. Yeah, I'd love to hear more about how you see that happening in practice, those different domains, but we should we should move on.
It sounds easy, but it's not.
Yeah. No, I'm curious, but we should move on. So yeah, this takes us to our last topic, which I'm also very excited for. And we're going to have that kicked off with Hannah Kerner.
All right. Hi, everybody. Hope you can hear. Let me share my screen. Okay. So today I'm going to be talking about a project that we've been working on over about the last year called Fields of the World, or FTW for short and fun. So this is a new machine learning benchmark data set for doing agricultural field boundary segmentation on as many continents as we could for now. So this is a collaborative work between my lab at Arizona State University, Microsoft AI for Good, WashU St. Louis, and Taylor Geospatial Engine. So when we talk about field boundary data sets, what we're talking about are these digitized polygons of field boundaries or individual field instances in agriculture. And the reason this is of great interest to many, many people is that there are a huge amount of applications that really either require field boundaries in this format for an agricultural area or are made a lot easier if you have these boundaries. So if you want to do things like estimating the yield that will be harvested at the end of the season, or the conditions in a field, pests and diseases, what kinds of practices like tillage practices, for example, a farmer is using, you need to have that boundary unit defined. There's a huge number of use cases in measurement, reporting, and verification of different policies and programs. For example, the EU deforestation regulation, which requires ensuring that commodities, 7 different commodities sourced in the European Union have come from fields that have not deforested in a certain time period. So to do all of these things, we need to have these vector formatted polygon boundaries of where individual fields are located. And so given this huge importance, the Taylor Geospatial Engine created this field boundary initiative about a year ago to collect all of the field boundary data sets that were currently publicly available and standardize them using a common format. So we created the new Field Boundaries for Agriculture, or FOBOA standard, which borrows a lot of ideas from STAC. That involves putting all of these different data sets in GeoParquet as well, making them all interoperable, and then creating machine learning resources for automatically generating boundaries that fill these massive data gaps that we have across the world. So here I've circled in orange all of the places where we've collated existing field boundary data sets, and you can see that it is like just a tiny, tiny sliver of the globe. So we want to be able to use machine learning methods to automatically predict those polygon data sets where they don't exist from the satellite data, which is available globally. The problem with this is that machine learning doing this relies on having large-scale data sets of what these field boundaries look like in satellite data for us to train our machine learning models on, and evaluating or measuring progress on doing this task so we can continually improve methods for doing it involves having specifically benchmark data sets that we can use for consistently training and evaluating models on this task. So there are a few of these benchmark data sets already, but they're extremely geographically limited. They're mostly in Europe and generally covering very homogeneous fields like those that you see on the left in France, which are, fairly easy to see even for a non-expert to identify where the boundaries are in that left-hand image. But on the right, you can see a lot of examples from different places in the world in satellite data where the boundaries get much more difficult to define. So there's a huge amount of diversity and complexity globally in these field boundaries that are not captured in existing data sets. So with that motivation, we created this brand new data set called Fields of the World, which is the largest machine learning data set for field boundary segmentation that exists. It's an order of magnitude larger than the next largest data sets and has nearly 80,000 samples in it. We cover 24 countries on 4 continents. So we essentially used all data sets that we could that were available at the time and met our quality standards. And it follows this new FABOA standard that I mentioned we created as well as part of the broader TGE project. And you can read more about this data set in our paper, which is on archive right now and will be published at the AAAI conference, shown here on the right. But I'll give you a preview here. So in the data set, we have samples that look like this, these little tiles or patches of satellite data from all these different countries. And for the labels, we've taken those GeoParquet vector files and rasterized them and turned them into these label masks where we have semantic segmentation masks, which means all the fields and their boundaries and interiors are identified, but we can't say which individual fields are which. They're just all lumped together. And we also have instance segmentation masks, which do separate the individual field instances. And we also have for each of those label masks, the corresponding satellite data from Sentinel-2 at 2 different points in time. So we tried to get these contrasting views of the fields in order to better reveal where the boundaries are for each field. And those approximately correspond to the planting and harvesting timelines of each of the regions. So as I said, this is the largest and most diverse data set that's been created. We have a lot of fun visualizations showing the diversity of field boundaries globally in the data set. But the important thing to note is that our data set spans a really wide range of field sizes and field shapes, including their number of vertices and their polygons to the orientations of them and all kinds of other morphological features, and also has much greater geographic coverage than any other data set. So what this means is that when we train machine learning models on fields of the world compared to more geographically limited or diversity limited data sets that we had access to before, we get better results on new regions that the model hasn't seen before. So the model is able to learn from this large fields of the world data set a much broader, more generic representation of what fields can look like globally. So when we tested on new regions like India or Cambodia or Vietnam in these examples, we get much better performance than training on more geographically limited versions of the data set. And we've seen some pretty good results in some really challenging areas. For example, in Ethiopia, where field boundary delineation is extremely difficult, without any additional training data in that region, just using a fields of the world model out of the box, we get some pretty promising starting performance, which is in the bottom right. So in the GitHub repo for Fields of the World, we also include a lot of command line tools for downloading the data set. So you can download subsets of the data set for different countries or different licenses that the data have. You can download data to use for inference, so making predictions on new Sentinel-2 tiles in a new region. We have tools for running that inference, so predicting with pre-trained models that we package in the GitHub repo, and then polygonizing those data sets back into a GeoParquet or Polygon format. So in the future, over the next year or so, we're going to be working on actually using this to create new field boundary data sets in those regions where we saw no data sets already existing in the beginning, to try to fill in these data gaps globally, and trying to improve the model fine-tuning protocols. As we get new data, we can adapt the models as efficiently as we can to new regions and new labels. And we're already thinking about extending the data set in a second version, hopefully in the next year or two, with more boundaries that have come out and other satellite data sources. Thank you.
Awesome. Ivar?
Yep. Share. So you can hear me? Yeah, that's good. So I have a presentation that's closely aligned to Hannah's work. I'm going to talk about the cloud native field boundaries and the FIBOA project mostly. Many different parties in the world, they digitize field boundaries. So government and other organizations. And well, these are the three most important points I wanted to make. The FIBOA project enables data sharing and reuse. And cloud native formats facilitate the serverless sharing of these data formats. So you can share them easily in a cheap way, and people can use it for different use cases. So Hannah already explained what are field boundaries, and I got some great pictures on this. So they're the delineation of the farmers' fields, and they look differently in many different countries, and many different places have this type of vector data. So it's like the polygon that marks the border of a farmer's field, mostly. So why are they relevant? And I think Hannah already explained parts of it, but it's really very relevant. The simplest use case is already like, it's easy. You can identify a field, you can talk about it. It doesn't have an address. It has some georeference in place, but if you have this vector data available, you can identify it and use it in all kinds of different administrations. And what you can do is you can look at spatial and temporal in-field data differences. So if you have other data sets that have also a spatial component, like satellite imagery or elevation models, you can analyze in-field differences, and this can help you assess what you need to do on a specific field, if you need to do variable rate applications, or if you need to treat different parts of the field differently, or whether you have a problem in a field. So this is why field boundaries are handy to have. And also spatially, for instance, what's relevant as use case that is being used a lot for determining what to plant in the next year is if you look at the crop rotation. So if you can see what has been a crop in the previous year of over a longer period, you can assess what's a proper crop to plant in the next year. And also for regional statistics, like differences within a specific region, you can use it to analyze it if you have the crop field boundaries. So I already said, like lots of different organizations, they digitize these data, like governments for different use cases, farm management solution providers. This is actually where I have most knowledge on, because I ran a farm management system company for over the last 13 years, and I've been working with 10,000 of farmers and helping them digitize different types of information, and using, well, having field boundaries actually facilitated this and made it a lot easier to do certain things, and resources like we've seen in this previous presentation. So what happens if these field boundaries are digitized is sometimes, if you're lucky, these data sets are shared on the web. So many European governments They share their field boundaries, including crops and all kinds of other related data. They share these data sets somewhere on the web, if you're lucky, as open data. And the problem is, if you want to use it, if you want to use these different data sets, even though they're high quality, because sometimes they're hand-drawn, they're validated by looking at other different data sets, so they really have high quality, but they're hard to find because like every country or even like every province sometimes has their own open data portal. They have different languages. Sometimes you don't speak them. They have different metadata, and they're all in different formats, like from GeoPackage to you have what, and projections. And sometimes even if they publish consecutive data sets over time, they use different formats and different column names. So it's like a lot of hassle to start using this type of data. I had been doing this for a long time, and this is when like last summer, I ran into the FIBOA project. And one of the goals is to enable sharing of these data sets. So what is this FIBOA? If I want to state it in 3 points, like one is the specification of how to share and transform data in a way that is the same for all different types of data for field boundaries. The Field of the Worlds initiative that we just have seen by Hannah. And we publish tools and data. Like what we do is like we identify data sets. Where are they located on the internet? What's the metadata? What's the license? What are the properties that are there? We write open source converters, so you can convert the original data set from shapefile or WFS or something else to a FIBOA data set. And all the FIBOA data sets are shared as open data on source code. I will have some URLs later. So if you look at the specification actually describes a GeoPackage or GeoJSON collection should have some type of metadata, like what's the FIBOA version and the extensions. And for each feature, we define, you should have an ID and geometry and some other optional attributes. The core specification is kept very simple because extensions allow you to add more things. For instance, a crop extension I created 3 months ago aligns very well with the European data sets. Like they all use their own code list for identifying codes, but what they do mostly is use a code and a name for a crop. So if a shared FIBOA data set implements the crop extension, every feature declares what crop code list is being used and a name and a code for the crop. So this allows you, if you have data sets from multiple different countries, to use them in the same way. So there's a longer list of extensions, but I think this is still growing. The other part I was talking about is the data sets that are shared. So we have identified open data sets that have a license that allow you to share this data in many different countries. There is a huge focus on Europe because of the Common Agricultural Policy and the INSPIRE guidelines. So these require all these governments or paying agencies to digitize these field boundaries, and they're supposed to openly share them. So these are the openly shareable field boundaries, and together they form like 120 million field boundaries that have high quality. And you can access them on the site. You can download the package files, and we have a visualization that actually works with tiles, PM tiles. So we share the data sets on the source code. So, and one of the points I want to make, and I understand the audiences might already be aware of it because it's all about cloud native, but I'm really enthusiastic about this part because I think the world is changing by having these great archival formats available. And even though we don't share like the 400 terabyte formats, like the data set is a lot smaller, still it will disrupt the way you can share your data. Because previously, if I would share raster data or vector data, I would do that with a setup, with an infrastructure where you would have some software component like map server or GeoServer or an Esri server that transforms your data from the original data store to something that a client is capable of consuming, like a web browser or a QGIS or something else. And these new or relatively new cloud native formats allow you to do that without a server in between. So these Parquet files that are being stored, they're accessible directly, and you can download a small chunk which is relevant for you. And I think it becomes a lot easier to share data sets because the infrastructure of sharing this data is a lot cheaper than running your own infrastructure with specialized software tools. So these are the points I want to make, that the infrastructure of having only the data in shared object stores is so much easier and to scale as well, and to host than having GIS servers there. The data has become like a lot smaller. GeoParquet actually, it's amazing how small data sets can become. And still you allow clients to download a part of a file without doing a lot of work. So this is where I read somewhere that people call this serverless. It felt for me a little bit like the cloud, right? It's just someone else's computer. Serverless is not really serverless, but at least it's with object storage where you don't have to do a lot of work for. So I think it's a really great new way of using the data, sharing data. So this is what I talked about, and these are the links of the data and of the project. This is where you can find the code and the data sets. This is what I wanted to show for today. Thanks.
Amazing, thank you. Are there any questions from the attendees? Please go ahead and go off mute or raise your hand and I can call on you. Okay, well, my question I think is for Hannah. I know that you have a lot of experience with different machine learning applications in earth science, and I'm just wondering if you see this pattern that was used for field boundaries being a good pattern to use for like other object sort of identification, classification problems.
Yeah, that's a great question. I think for sure, like this format is kind of standard for creating benchmark data sets for machine learning and remote sensing or geospatial applications. But I think we've definitely underutilized all of the vector data sets that are out there in the universe, you know, even on things like OpenStreetMap and various places where they're just scattered. So I think there's a lot more opportunity to create data sets in the future for enabling that. And that's especially going to be useful as we get more traction with foundation models that can more easily solve a lot of different tasks. And we want to be able to evaluate how well they do in a lot of different tasks.
Awesome, yeah. Okay, unless there's any other questions, I'm going to wrap up. So I definitely want to thank all of the speakers for joining today. Thank you so much for your collaboration and coordination on this. It was sort of a new format, so I appreciate you trying it out with me and being flexible, and especially Sean, who came in to help at the last minute with an additional presentation. So yeah, and then I'm just going to share my screen real quick to share the notes. Yes, so Rich, or sorry, was that Rich? Who was that? No. Leilani probably. The presentation. So yeah, if the presenters could please share their presentations with me, if you're willing to make them publicly available, they will eventually be in this folder. There is at least the I'm going to copy this link. I see at least the ice chunk presentation in there. I will add the others if the presenters could share them with me. And then I just wanted to also wrap up by sharing some resources. Okay, so going to our notes document. Sorry, there's a lot of things that are popping up at me right now. Here we go. Okay, so you should have a link to the notes document, and I just popped a bunch of links in here if you want to learn more about all the technologies that we talked about today. Here's, I'm sure it's an incomplete list, but a link to Virtualizar, which Sean talked about, IceChunk, which Ryan talked about, and there's some other great presentations he gave on IceChunk linked there. You can learn more about GeoParquet, a lot of resources on fields of the world. And then finally, a link to the conference, the Cloud Native Geospatial Conference that Michelle mentioned at the top, which will also feature, like she mentioned, cloud native use cases. So yeah, thank you all so much for joining. It's a great session, and thank you to our presenters. So yeah, and hope you all enjoy the rest of ESIP.